Thank you, Aisha. Can everyone hear me? This thing is funny. All right. So yeah, let's talk about my project this summer. So this summer, I worked on measuring apatite chemistry with potential implications for apatite helium geochronology. So let's just start off simple. What is helium dating? I'm sure you've heard of uranium-lead dating, maybe even fission track dating, but helium dating might sound a little unfamiliar to some of you. So let's just look at the breakdown of uranium to better understand it. As you can see, in each step in the radioactive decay chain of uranium, a helium nucleus, or alpha particle, is produced. Now, we can actually quantify this helium along with the uranium and thorium and get a state. And we do that using the helium production equation. Yeah, it doesn't show up. We have our helium, we have our uranium, we have our thorium. We plug all our values in, and we solve for T, which in our case is time. So at this point, helium dating is actually a well-accepted geochronology tool. And it's unique because it offers a cooling history of a region. And it does that because an apatite, which is what we helium date, has a closure temperature of approximately 70 degrees Celsius. So what that means is that when an apatite cools to that threshold, any helium that the apatite is producing actually gets retained within the apatite. Therefore, we can measure the helium and predict the cooling pathway in which the apatite likely cooled, thereby getting a cooling history of the region. So here's an example of a cooling pathway. If you focus on the bold line labeled TT path for time temperature, you'll see that this apatite cooled very rapidly and then stayed stable for about 40 million years. This is usually the result of some tectonic process, such as like a region thrusting upward and the apatite cooling very fast. In contrast, we have slow monotonic cooling. So here, the bold TT path is a steady line, and it's generally indicative of just natural erosion of the surface and slow exhumation of the apatites beneath. Now, with any technical process, we're going to have some concerns, we're going to have some issues. And one controlling factor that's already been identified is radiation damage and annealing. And this has been identified and accounted for. But it turns out that an apatite's chemistry actually is a controlling factor for radiation damage and annealing. But apatite chemistry hasn't fully been explored on how it affects helium dating. Now, I'll get back to that later, but first let's just look at radiation damage and annealing first. So I want you to imagine apatites like a beautiful, complete jigsaw puzzle. And what happens over time is that with natural radioactive decay, apatite begins to accumulate something known as radiation damage. And this radiation damage comes in the form of traps, or holes in our puzzle. And what these traps can do is that these traps can actually retain more helium than an apatite naturally would without the traps. Now, thermal annealing, on the other hand, reverses this process and fills in those traps, fills in those holes in our puzzle. Both of these processes happen naturally throughout an apatite's lifespan, so in order to account for both of them, the radiation damage accumulation and annealing model, or RDAM, was developed by Becky Flowers, who's my mentor, and her team. The only thing is that this model doesn't take into account apatite chemistry. So now I want you to imagine that jigsaw puzzle again, and we're annealing our apatite and we're putting the puzzle pieces back. But imagine that those puzzle pieces have been altered a little bit. That would certainly make putting the puzzle back together harder, or in our case, make annealing take longer. Well, it turns out that the formula chemistry for apatite actually can be altered by lattice substitutions. So as you can see in the N group, fluorines can be replaced by chlorines, or even calcium can be replaced by manganese or iron. And changes in the crystal lattice can alter the way in which the apatite anneals. And the fission track community, which is a related thermochronometer, but not the exact same as helium dating, but their previous research showed that apatites with high chlorine contents were more resistant to annealing. And Becky Flowers and her team, who came up with the RDAM model, suggested that this same exact effect could hold true for helium dating as well. So what did I do? Well, that's what I tested. I have my two study groups here. I tested two areas in which apatites with contrasting chlorine contents were found. One was Mount Powell in the Gore Range, Colorado, right here. And if you look at the top graph, you'll see elevation versus date. And majority of the dates fall below 50 million years, but there is one anomalously old date of around 280 million years that just doesn't make sense. And that was collected by Charles Naser in 2002. And he tested the chemistry on that sample, and he found that it had much higher chlorine content than the other samples. And this was with fission track research. Now, on the bottom, we have 2 samples from the Canadian Shield with a similar effect. So if you look at the blue markers, or sample 82, the age is just around 400 to 500 million years. And the red markers seem to almost have bimodal dates, with a cluster around 400 million years and another cluster around 650, and then one up to 950 million years. What's important to note about these 2 samples is that they were collected right next to each other. So they should have the same exact dates, but they don't. So we tested these 2 samples to see if the chlorine content and helium data had any correlations. So what did we hypothesize? Well, we thought that the chlorapatites that we collected would yield much older dates than the previously published dates. And we think this because we think that chlorine is going to have this resistance to annealing effect. And if there's a resistance to annealing, that means that there was more time for radiation damage to accumulate. And if that happened, then we're going to yield older dates. So what did we find? Well, we had to start off by the standard helium dating process of apatites. So when we're selecting our apatites, we're looking for what we call high-grade apatites. And that includes large crystal size, euhedral crystal shape. So apatite is hexagonal, so when you look on it, you want to see 2 pyramids on the top and bottom like you see on the left side. And you want to see it free of inclusions, so any scratches, bubbles, marks, anything like that, as you see on the right side. Generally, these inclusions can often be smaller minerals crystallizing inside of our apatite, which would just totally throw off our helium date. So we don't want any of that. Next, we had to get the chemical compositions, and we did this using 2 different methods. We used an electron microprobe at the University of Colorado Boulder. So I mounted the grains in epoxy and polished them real nice, and then pretty much shot a precise beam of electrons at our grains, and depending on what came back, we can determine the chemical compositions. We also used another method called laser ablation ICP-MS, and this was over at the USGS in Denver. So this machine actually shoots a laser which bores a hole through our apatite grain, small hole, and depending on what comes out, the ICP-MS can process a much wider range of compositions. And this actually was very useful. You'll see why later. So we got our dates by measuring the helium, uranium, and thorium. So we have our helium extraction system, which gave us our helium-4. We have our ICP-MS, which gave us our uranium and thorium. We plugged it into our equation, like I said before, and we got our dates. So what did we find? Well, here's that Mount Powell graph I showed you earlier. And here are all the dates that were lower than 50 million years. And our dates are the orange triangles. Now, we dated the same exact sample that Charles Naser got that anomalously old date for. And 2 of our samples actually yielded below 50 million years, which is the regions expected. And one of our dates was 210 million years, anomalously old, just like he had received. So we're thinking it's got to be chlorine. When he tested it, he found chlorine. We're thinking it's got to be chlorine too. So we tested the chemistry. And where's my graph? It's not showing up. Okay, well, for some reason my graph's not showing up. But here's what you need to know. I can explain this without a graph. Imagine that chlorine content is on the y-axis and fluorine is on the x-axis. So as you get higher, you have higher chlorine. That top circle is the data point that Charles Naser received. It was about 2% chlorine. This is about the bottom of the y-axis. This is maybe 8 samples of chlorine grains that we sampled for chlorine. We got little to no chlorine at all in all of our samples. So now this left us puzzled. And even the Canadian Shield samples, which you can't see here, there was a difference between the 82 and 84, but it was nowhere near significant as much as we had expected or as was previously reported. So now we're puzzled. It's not the chlorine, so we decided to take a different approach. We looked at a value called RMRO, and what RMRO is actually a proxy for annealing that doesn't just take into account chlorine content, it takes into account a wide range of lattice substitutions. So that means the manganese, the iron, rare earth elements, anything that could be substituted into an apatite. So if you see on our left, we have chlorine in atoms per formula unit. We had to convert it for this particular graph. And we have RMRO on the bottom. And the higher the value is, the faster the apatite annealed. And there's a lot of markers and colors here, but what's really important to note about this graph is that the gray bar represents the R-MRO value of a typical apatite as established by Carlson in 1999. Now, almost majority of all of our grains yielded values below that. So what that means is that our samples were more resistant to annealing despite the range of chlorine content or little to no chlorine content that we got. So what does that mean? Well, here's what we concluded. We tested our Mount Powell sample, and we got the anomalously old date that Charles Nacer got, but we didn't get the chlorine content we wanted. So that left us thinking chlorine isn't the only thing responsible for the resistance to annealing effect that we're seeing. And our R-MRO values showed that our apatites were more resistant to annealing. So this kind of leaves us thinking that the resistance to annealing effect is actually due to a menagerie of elements that can be substituted in. And last, future work helium would consist of helium dating these grains, which we just calculated the R-MRO values for. And that's actually already underway. So I'd like to acknowledge everyone who's made this study possible, my mentors, CU faculty, the USGS, RECESS, Aisha, of course, UNAVCO, and the National Science Foundation. Any questions?
Thanks, Brandt. And if you would like to see that missing graph, come to his poster tomorrow, because it will be there.
Yeah, I don't know what happened there. That is weird, because it was there yesterday.
Any questions?
Kaylee?
Hi, that was a great talk. It was awesome, even without the graph. I was wondering if you had any speculations on why you would get apatite with these different compositions.
As in why there would be substitutions?
Yeah, or like, is there any reason why you might have a weird apatite in these samples versus a more typical apatite?
I'm not exactly sure what would cause it per se, but I can say that it's definitely more rare than just a typical apatite. Like even a high chlorine apatite is very rare to find in general. So I mean, we're just looking out for those contrasting chemistries in apatites.
Cool, thanks.
Great talk, by the way. You mentioned about taking out the apatites and mounting them. How did you extract them from the rock? Or is it on a thin section, or?
So we used the same exact sample as that Charles Nacer had. So he had already had the separate for us. So I didn't do the whole milling process and all of that, unfortunately, which I did want to do. But no, I transferred the grains onto a piece of double-sided tape, and then filled it with an epoxy, let it cure, and then polished them, and then looked at it under the electron microprobe.
Any other questions? No? All right, great job, Brandt. Thank you.